Hey everybody, we've got the basics of dimensional analysis. Now let's take it up a notch. Let's solve some new problems, maybe some that aren't even like notably chemistry related. So whenever we are looking at a new problem, sometimes we will be given the equalities that we need, and other times we will need to look them up, say, on our metric conversion list. So that's one thing to be aware of. Sometimes we'll be given information, sometimes we need to go get it on our own. What we should be aware of is that in every problem, only one thing will be known. You can't have more than one thing. You can't have two knowns, right? Or three knowns or whatnot. You'll only ever have one known. You'll have one unknown, and everything else will be a conversion factor that needs to be used along our journey. So here are our steps for going along and problem solving. So first off, we need to read a problem and we need to analyze the information that's given to us, and then we can identify some of the knowns, unknowns, etc. We'll do that in a second. We also need to formulate a plan. So we need to decide which conversion factors we're going to use, and then we're going to actually do that calculation. So we're going to compute by plugging in those conversion factors and going from there. Once we've done that, we're going to evaluate our answer and we're going to decide, is this reasonable, right? Like, does this actually make sense? And if it doesn't, then we need to go back and we need to check the conversion factors that we've used. So let's do this. Let's take a stab at it. If you want to read number one, pause the video, feel free to do that, and then we can rejoin. So let's identify what we know here. What we know in number one is that in order to make these rails at the iron foundry, we are going to need 646 metric tons. How do I know that's my known value? Well, you'll notice that it's not an equality. It's just kind of a number that sits by itself. And ultimately, at the end of the day, what do we want to know? We want to know how many ladlefuls of iron are we going to need to make those 646 metric tons. And then there's some interesting information given to us. I'm going to underline this in green. So it turns out that 1 metric ton is equal to 1,000 kilograms. That's an interesting conversion factor that we'll need along the way. And we are also told that a ladleful can hold 8,500 kilograms. So you might be able to kind of plan out in your mind how this is going to work. We're going to go pink, green, green, blue, and let's see how we get there along the way. So I'm going to give myself a nice long fraction line for our conversions. I'm going to start with what we know, that's in pink. We know that we have 646 metric tons. And I'm going to abbreviate metric tons MT. And so before I do anything else, I might know nothing else about the problem. I know with certainty that MT has to go on the bottom of my next line. And if MT has to go on the bottom, that actually helps to guide me towards where I need to go next, right? Because I know right there in green that a metric ton is equal to 1,000 kilograms, right? So that's a conversion factor that we have. 1 metric ton is equal to 1,000 kilograms. So you might already be able to see where this problem is going. If you don't know where this problem is going, just doing that conversion can help you get somewhere, because once you've canceled out these units, metric tons, you know that the next thing in line is that your kilograms have to cancel, right? You have a kilograms in the numerator. We darn well better have a kilograms in the denominator to cancel it out. So where can that take us? Remember, we're on a journey towards ladlefuls. And lo and behold, look at this number up here in green. We are told that 1 ladle can hold 8,500 kilograms. So 8,500 kilograms is equal to 1 ladleful. And now let's cancel out the units that we have. So the units that we have are kilograms and kilograms. Those cancel. You know you are done once you've arrived at the number that you're trying to get to, or more specifically, the unit you're trying to get to. We want to know at the end of the day how many ladlefuls. We've identified ladlefuls. It's uncanceled out. That's the number that we want to have. My line is clearly way too long, so let me redraw that. My fraction only needs to be this long. And if you do the math here, remember you're multiplying numerators, dividing by all of the denominators put together, you will get 76. But remember, we have to check our sig figs. So we started with 3 sig figs. The sig figs that are part of definitions don't count, right? We said those are infinite. So really we only care about the starting number. If we want 3 sig figs out of 76, there are only 2 numbers. How can we give it a third? Well, we're going to put 76.0 because a decimal point and a trailing 0 makes that significant. So 76 ladlefuls is our final answer. Let's try again. Again, if you want to pause the video and take this one on your own and then, replay the video, feel free. So we're looking at this car, this automobile, and it's using 0.25 milliliters of oil for every kilometer it's driven. We know that that's a conversion factor because you'll notice it's 0.25 milliliters for each kilometer, right? So if it's kind of an equality like that, that's conversion. It says how much oil, that must be our unknown, in liters, is consumed if the automobile is driven 20,000 kilometers. That must be our starting value, right? It's not an equality. So let's start there. Let's start with our 20,000 kilometers and see where it takes us. We have 20,000 kilometers on top. We know before we do anything else that kilometers must be the unit that goes in the denominator of the next fraction. Now we're on a journey towards liters, and you'll notice that liters is a volume, and we right now have a distance, right? This is a volume, we have a distance. Ultimately, in our problem, there must be some conversion that takes us between distance and volume, and there it is in green. We know that every one of those kilometers requires 0.25 milliliters of oil. And so you might think, well, wait a second, I'm done, right? Because it says how much oil. But if you're really tricky here, you realize that it says in liters. So our last step is that we need to take those milliliters and we need to get rid of them somehow. How do we get rid of them? Well, we put them on the bottom. We can put milliliters of oil down here. We want to get to liters at the end of the day on top. And so we know that conversion. We know there are 1,000 milliliters in every 1 liter. And once you've done all of that, you'll notice that things cancel. Kilometers cancel, milliliters cancel. You're left with liters. If you do the math, again, multiply numerators, divide by denominators, you'll end up with 5 liters of oil. And if you come back to the beginning, 20,000 looks like a big number, but in terms of known numbers, known values, this only has 1 sig fig. None of those zeros are significant. Now they matter, they're there, right? But they're not what we call significant. They're not known measurements. So that's why we only have 1 significant figure in our answer. We are going to need 5 liters of oil for this journey. Let's try one more. Hopefully you're healthy and drinking your water each and every day. You're drinking 8 glasses of water every day. That looks like an equality, 8 glasses per day, right? So that's going to be in green. It says each glass contains 300 milliliters. That's another equality. 1 glass is 300 milliliters. It says how many liters, that's what must be what we're after, will that person consume in a year? And it looks like there's no other number, right? So like, what the heck is going on here? What's our known value? We don't seem to have a known value. But notice that this says 8 glasses per day. And so this is actually really tricky, right? How many will they consume in a year? Well, we know something about a year, don't we? We know that a year is 365 days. And if we get to days, one of our conversion factor uses days. So that must be a really good place to start because we can cancel out days. So let's see what happens. I'm going to set myself up a really long fraction line. We have days in the numerator of the first fraction. That means days has to go in the denominator of the second fraction to cancel out. And we know from one of our conversion factors that we are going to be drinking 8 glasses of water for every 1 day. Once we have glasses of water, we're trying to get to eventually how many liters, right? So if we're trying to get to liters, glasses isn't a volume, it's like a counted number. We want to know how many liters. Well, turns out there's another conversion factor, right? We know glasses has to go in the denominator to cancel out. And we are told that 1 glass happens to have a volume of 300 milliliters. And so that's really excellent because now we're in volume. The only problem is we want liters, right? So we actually know something further. We can extend our line. We know that we need milliliters in the bottom, so it can cancel out. we know we're trying to get to liters at the end of the day, and we know that there are 1,000 milliliters in 1 liter. And so now you can go through and you can check your units. You have days on top, days bottom, glasses, glasses, milliliters, milliliters, everything cancels. You're left with liters, that's where you want to be. If you do the math, remember multiply your fractions, multiply your numerators, divide by your denominators, you'll get the value 876 liters that you're drinking in that year. You are starting with 3 significant figures, really, we'll say, even though it's a counted number. So this is kind of weird significant figure-wise, but we're going to end with 3 on this one. We'll get into more details on some of those confusing significant figure problems a little bit later on in the year.